This video is going to show you the molar conversions heart chart, which is a summary for the main molar conversions that are one step. It is not a substitution for understanding how unit conversions work and for understanding the core of this chemical concept, but it does help you to summarize what those main three molar conversions are as far as how to get into and out of the mole. There are three standard ways to get into or out of the mole, which is the central heart concept of chemistry. The first way is mass, measured in grams. The second way is particle count, which is simply a count of the number of usually atoms or molecules. When we say particles, we're talking about usually atoms or molecules, sometimes protons or electrons, just number of small things. And then the third way is the volume of the gas at STP, measured in liters. We'll talk about what standard temperature and pressure means in a bit. We're going to zoom in on the moles to mass conversion first and talk about what that bridge really is. First, you have to understand that there's an important concept called molar mass, and molar mass relates to how many grams, or the mass of a compound when you have 1 mole of it, which is 6.02 times 10 to the 23rd particles. So calculating molar mass is pretty simple. If you have a compound such as NH3, which is ammonia, then to calculate the molar mass it would be 14.00, which is the average atomic mass of one nitrogen molecule in AMU, plus, one nitrogen atom, plus 3 times 1.01. This approximates to around 17 grams per mole. This is the molar mass. And as you can see in the units, you have grams and you have moles, which is the bridge between mass in grams and moles. If we were to calculate the molar mass of N2F2, which is dinitrogen difluoride, grab your periodic table and you'll see that 1 nitrogen is 14.0, so 2 nitrogens would be 28, and you add, do not multiply between different elements, you add between different elements, and I would have also 2 fluorines. Fluorine is 19.0. So 2 times 14 plus 2 times 19 gives us a total molar mass of 28 plus 38, which is 66 grams per mole as the molar mass. If you have a certain number of moles of a compound or an element, say you have 2 moles of N2F2. If you have 2 moles of something and you're trying to convert from moles to grams or mass, then what you'd have to do is look at your units. Moles of N2F2 will have to go on the bottom to cancel out, and you're going to grams of, in this case, for example, N2F2. The molar mass of the compound goes next to the G. It'd be 66.0. And remember, that is the mass of a single mole. As you can see, to leave the mole and go into mass, you need to multiply by the molar mass. So leaving the mole and going to mass, you multiply by mm, which is my abbreviation for molar mass. Of course, the opposite, if you have grams of a particular compound and you want to find out how many moles of compound that is, then you need to divide by the molar mass. So if 1 mole of N2F2 has a mass of 66 grams, then 2 moles of N2F2 would have a mass of 2 times 66 grams. The next piece is pretty important too, and that is how to convert between moles and particles. 1 mole of anything, so 1 mole of anything is about 6.02 times 10 to the 23rd things. Those things in chemistry are usually going to be atoms or molecules. Occasionally, electrons, protons, or some other subatomic particle. A mole of any macroscopic thing like donuts, or basketballs, or buses would be extremely large, the size of the planet or bigger. So this number is humongous, which means that it represents a certain number of very small things. It's kind of like a dozen. 1 dozen is defined as 12. 2 dozen is 24. 1 mole is this massive number of things, and those things are usually going to be called particles. This number is called Avogadro's number. Avogadro number. Occasionally, you will see Avogadro's number abbreviated symbolically as N with the subscript A. Suppose I have 2 moles of water, and I want to find out how many water molecules that is. A molecule, of course, is a type of particle. I would put moles of water at the bottom to cancel it, and go from moles of water to molecules of water. We know that 1 mole is 6.02 times 10 to the 23rd number of particles. If 1 mole is this, then 2 moles would be 2 times this. And of course this is Avogadro's number. As you can see, to leave the mole, again, we multiply. In this case, we are multiplying by Avogadro's number. The opposite of multiplying, of course, is dividing, which means that if I have a very large number of particles, and when I find out how many moles of particles that is, I would divide by Avogadro's number. And as a reminder, Avogadro's number is 6.02 times 10 to the 23rd power. And that's a number that you absolutely have to memorize. 6.02 times 10 to the 23rd power. The last part of the heart chart is the relationship between volume of a mole, or molar volume, at STP for a gas. It's very important that you understand that only gases can use this part of the heart chart. And in addition to it only being a gas, you have to realize too that only gases at very certain conditions can use this number. Until you learn about the ideal gas law and how to determine pressure and temperature and how to use them mathematically, you just have to memorize this one. To find out the volume of 1 mole of a gas, you multiply by 22.4. The opposite case, where you have the volume of the gas at STP and you want to find out how many moles it is, of course you would divide by 22.4. We're going to talk real quick about what STP really means. STP stands for Standard Temperature and Pressure. What that means in a little bit of basic detail is that standard temperature is 0 degrees Celsius for a gas, which we know is 273.15 Kelvin. That is what standard temperature is. If a gas is warmer than this, then it will expand and take up more than 22.4 liters of space for every mole. If a gas is colder than this, then the gas will contract and take up less than 22.4 liters of space for every mole. Standard pressure is 1 atmosphere. An atmosphere is a unit of pressure. That is also approximately equal to 14.7 psi for American pressure units, which is pounds per square inch, also equal to approximately 760 torr, which is 760 millimeters mercury, also approximately equal to 101.325 kilopascals. All of those are units of pressure. But all that really matters is 0 degrees Celsius and 1 atm. Here's one worked example of how the molar volume of a gas at STP can be used. If you have 44.8 liters of methane gas at STP, how many moles of methane do you have? You look at your unit, which is liters of methane, and you put the units at the bottom. That way they cancel out. You're going to go from liters of methane to moles of methane. The relationship we just learned is that 1 mole of any gas at STP, standard temperature and standard pressure, takes up 22.4 liters of volume, liters of space. 44.8 divided by 22.4 gives us 2 moles of methane. Looking at the entire heart chart, we can see that the heart chart summarizes what the math tells us, but it is not a substitute for understanding how units work and what these units are really talking about. So if you're ever in a bind, then look at the heart chart and think about what it means on a molar conversion basis. If you are at any one part of the heart chart, and there are 4 parts, you can have mass, you can actually already have moles, you can have volume of a gas at STP, volume of a gas at STP, remember, or you can have number of particles. If you have any one of those 4 pieces, you can calculate any other set of the 4 pieces of the heart chart. I'll give you a few examples of that in a second. Looking at the heart chart, you can see that every time you leave the heart chart, you multiply. So going from moles to anything is multiplying. Every time you go into the heart chart, going into the heart, you divide. Here's a 2-part practice problem. Suppose you have a container that has a total volume of 37.5 liters, and that container is filled with methane gas. So methane's formula is CH4, and it's a gas. If this container is filled with 37.5 liters of methane gas, how would you find the mass of the gas? And by the way, this methane gas is at standard temperature, 273 Kelvin, or 0 degrees Celsius, and standard pressure, STP. Because the gas is at these conditions, you're allowed to use 22.4 liters per mole as your conversion factor. We know just one thing, and that the gas has a volume of 0.5 liters. I will put CH4 here just to make the units more explicit. I've got 37.5 liters of methane over 1. I'm asked for the mass, so I'm going to go from liters of methane. And I cannot just go from liters of methane to moles of methane. The whole point of the heart chart, as you can see, is that you cannot go from any one part to the other part without either stopping at the mole or going through the mole. Because I'm going from volume of a gas at STP to mass of a gas, I have to first go through the mole. I'm going to moles of CH4. I do not need the molar mass right now, nor do I need Avogadro's number right now. This one step of the conversion in the first part of this problem asks us to remember that 1 mole of a gas at STP takes up 22.4 liters of space. My units have canceled out liters and liters top and bottom. This could be one type of problem where you're just asked to determine the moles of a gas given the volume. But we need to go one step farther. Now, I'm going to go from moles of methane to grams of methane. If you look back at our heart chart, the relationship between moles and mass is the molar mass. Methane is 12 for carbon, plus 4 times 1 for hydrogen, giving us a molar mass of 16 grams for every 1 mole of methane. Moles are gone, top and bottom, and when you get your answer, you will have the mass. 26.8 grams of methane makes sense because 37.5 liters is about a mole and a half as far as the molar ratio for molar volume, and 16 and 26.8 are related in the same way. So your answer would be 26.8 grams of methane, not grams per mole, not moles, not liters. If you look at the units that did not get canceled out, you got grams, which is a measure of mass. Given the same information and the same style of solving, I can answer the question, well, how many methane molecules are inside this container? Since this container is still 37.5 liters of gas at STP. I'm going to start off again with 37.5 liters of methane. And I put my units over 1 when they're one-dimensional in terms of the math. So 37.5 liters of methane. I'm going to go from liters of methane to moles of methane. Now the heart chart says to get into the mole, as we're about to do right now in this step, just like we did in part A, we need to divide by that special number. The special number remains 22.4 liters for every mole. So 22.4 liters per mole. The units do cancel out top and bottom still. But at this point, you're kind of in the heart chart. So if I scroll back over, we are currently at the part in the problem where we've made the transition from liters to moles, so we're in the center. And to leave the center, we have to think about what direction we're going. It would not make any sense to go back toward this, because we just left that position. In our problem, we are asked how many molecules of methane. So I need to leave the mole and go this direction, which means I will multiply by Avogadro's number. So, setting up my problem with my unit cancellation, I will do moles of methane at the bottom, and I will go toward molecules of methane. It's important to know that MOL is an abbreviation for moles, not molecules. we know that 1 mole of anything has this many particles, 6.02 times 10 to the 23rd. You will sometimes see that as 6.02 E23. It means the same thing. E means times 10 to the, and then you can put the power after it. That is oftentimes how your calculator will express it. Units are going to cancel, top and bottom. The units that will not cancel will be molecules. You can expect that there's going to be a whole lot of molecules of methane inside this thing. And that gives us our answer. 1.01 times 10 to the 24 molecules of methane. On a calculator, and sometimes shorthand via your hand, you might see it as 1.01 E for the times 10 to the part, and then the power right after it. I can't stress enough that the heart chart is simply a summary for what you should know about the units and what happens with molar conversions. It is not something you should try to memorize in place of actually understanding the concepts. Suppose you have a balloon filled with 0.177 grams of helium. Helium has a molar mass, by the way, of about 4. You could figure out really easily the moles of helium by doing one quick step, which is dividing by the molar mass of 4. You could also figure out the volume of the balloon by first converting your mass of helium into moles of helium, and then turning your moles of helium into liters of helium, with the understanding that this balloon is at STP. And lastly, you could go from mass of helium to first moles of helium, and then from moles of helium, you could find out how many helium atoms or particles are in here. And I would call those atoms of helium. As you can see from here, every time you do something with the mole in chemistry, you either stop at the mole or go through the mole. But the mole is the central heart part of conversions, and this is incredibly important for stoichiometry. So here's what I would task you to do, is to look at this example with the balloon and figure out how many moles of helium are in that balloon given the mass. Given that mass, what is the volume of the balloon in liters at STP, and given the mass, convert to moles and find the number of helium atoms inside that balloon. Also think about why that 22.4 number is valid only at a standard temperature and a standard pressure of 0 degrees Celsius and 1 atmosphere. If that balloon were to be heated, it would actually expand and be larger. If that balloon were cooled down to being less than 0 degrees Celsius, it would contract and be smaller. Hopefully you understand the heart chart and why it's not a substitution, but rather a summary of the main molar conversions. Later on in chemistry, you would learn about how to determine volume and mass and other things when the conditions are different.